Okay, G9C directional antennas. Which of the following would increase the bandwidth of a Yagi antenna? This is a Yagi antenna right here. Okay, this would be typically if you were looking at a horizontally oriented Yagi, you'd be looking down on this one. It has three major parts. The Yagi antenna has a driven element to which the power is applied here to the driven element. It is the reflector and the directors do not have power applied to them from the feed line. Okay? They pick up power from the driven element to do what they do in terms of making it directional. One way to increase the bandwidth of a Yagi antenna, to make it a broader band antenna, is to make the element diameters larger, and that will increase the bandwidth somewhat. What's the approximate length of the driven element of a Yagi antenna? It's a half-wave element. This driven element right here is a half-wave element. Which statement about a three-element single-band Yagi antenna is true? Let's take a look at the antenna drawing here as we look at these. The reflector is normally the shortest. No, you can see that the reflector is longer than the driven element, isn't it? And the directors are shorter than the driven element. Okay? The director is normally the shortest parasitic element. That is true. The directors, however many there may be, in this case it's a three element, so there's only one director instead of the three that we have in the picture, would be the shortest element in the antenna. Driven element is not a parasitic element. It's fed by the feed line. These are called parasitic elements because they get the energy that they need to do what they do, either to reflect or direct, by picking it up from the driven element. Okay? So the director out here on the front of the antenna is the shortest element, and the direction of the greatest greatest field strength for the antenna is in this direction. This is the direction that has the greatest field strength. Which statement about a three-element single-band Yagi antenna is true? Again, these are some things that if you have the picture of the antenna in your mind, you'll be able to sort this out. The reflector is normally the longest parasitic element. The reflector is the longest parasitic element. How does increasing the boom length and adding directors affect a Yagi antenna? The gain increases. The gain will increase as you increase the boom length and add more directors to the antenna. Which of the following is a reason why a Yagi antenna is often used for radio communications on the 20-meter band? It's a directional antenna. It helps to reduce interference from other stations to the side or behind the antenna. Okay, it's a directional antenna. So this is the front of my antenna, out where the directors are. I have a radiation pattern that looks something like this, where I have a strong signal response or a strong transmission strength out this direction and weaker in other directions. What does front to back ratio mean in reference to a Yagi antenna? The front to back ratio is the power radiated in the major radiation lobe, that's this right here, the front of the antenna, compared to the power radiated in exactly the opposite direction. Okay, so you're comparing this power to this power, and that's a ratio. It's expressed in decibels. The front power, the front gain to the back gain, okay, of the antenna, front to back ratio. What's meant by the main lobe of a directive antenna? It's the direction of maximum radiated field strength from the antenna. Again, using the same diagram, this is the main lobe right here of the directional antenna. What's the approximate maximum theoretical forward gain of a 3-element single-band Yagi antenna? Okay, they give you several answers here. Some of them may be tempting. The actual correct answer is 9.7 dBi. Now, I'm telling you more here than you need to know for the test. And if you want to ignore the next few words, feel free. Just know that the maximum theoretical forward gain of a 3-element single-band Yagi antenna is 9.7 dBi. They also give you 9.7 dBd. Now, dBi is a kind of an antenna manufacturer's trick to make the gain sound bigger than it is, because the I there means they are comparing that to something called an isotropic antenna. An isotropic antenna is a theoretical antenna which radiates equal power in all directions. It cannot exist in real life because you can't. It requires an antenna with dimensions of 0, and you couldn't radiate from dimensions of 0. But a dipole antenna has a gain of 2.15 dBi, and it's a realistic antenna for comparison. So this Yagi with a gain of 9.7 dBi would actually have about 7.55 dBd, because you would subtract the difference here with the dipole. The D here is comparing it to a dipole antenna now instead of the phony isotropic thing. But most antenna manufacturers do use dBi in rating their antennas. So you need to watch for that. And if they just say dB, then you can be pretty sure it's dBi. If they're rating it as dBd, they'll tell you, because the number will not be as high. Which of the following is a Yagi antenna design variable that could be adjusted to optimize forward gain, front-to-back ratio, or SWR bandwidth? The physical length of the boom, the number of elements on the boom, and the spacing of the elements. All of these are things that can be manipulated to change the various characteristics. All of these choices are correct. And there are computer programs that let you play with these things. The number of elements, the spacing of the elements, the length of the boom, all of those things can be computer calculated before you actually build the antenna and give you an idea of what you're going to get. You may want to get the best front-to-back ratio. You may want to get the widest bandwidth. You may want to get the best forward gain. And so you can calculate those things out or let the computer do the work for you as you design your antenna. What's the purpose of a gamma match used with Yagi antennas? The purpose of it is to match. Well, here you have gamma match, right? You got the word match right there, okay? So you have two answers here that have match in them. One of them happens to be correct. So throw these others out. And it's to match the relatively low feed point impedance to 50 ohms. Let's take a look at what a gamma match looks like. I hope this drawing will be meaningful to you if you haven't actually seen a gamma match. Here's the driven element of your Yagi right here, or a section of it. It actually extends out farther than this on both sides. The square thing right here is the boom of the antenna. So we're looking right straight down the boom of the antenna. Here is our feed point. And what we have here effectively is a capacitor, because we have a wire here or a rod that goes into an insulating sleeve. There you can see a little bit of the insulating sleeve. And then we have a metal cylinder around it, which is the other pole of the capacitor. And then that is connected to this driven element by this metal shorting bar. Okay? And by adjusting this, you can adjust the relatively low impedance, feed point impedance of this driven element to the 50 ohms that you want for your feed line. Which of the following is an advantage of using a gamma match for impedance matching a Yagi antenna to a 50 ohm feed line? It doesn't require that the elements be insulated from the boom. You can do this with an all-metal antenna. You can have your metal-driven element passing right through your metal boom here. No insulation required. The only insulation in the whole thing is in the center of the coaxial connector and between the rod and the cylinder on the gamma match. No other insulation in there. This will load that up and give you the impedance that you need. So it doesn't require that the elements be insulated from the boom. Approximately how long is each side of a quad antenna-driven element? How long is each side of a quad antenna-driven element? What's a quad antenna? Let's look at a picture. Okay, here's a quad antenna. This is the driven element. You can see that the feed line comes up, and it comes right to here and out to this wire that's stretched around these spreaders right here. Okay, and each side of that quad, each side of that is approximately a quarter wavelength. All right, back here we have a reflector, and you can see that even in this picture, which is not terribly accurate probably, the reflector looks larger, and it is larger. The element lengths are larger than on the driven element. How does the forward gain of a 2-element quad antenna compare to the forward gain of a 3-element Yagi antenna? They're about the same. They're about the same. So the 2 elements of quad compare to about 3 elements of Yagi. Now, with this in mind, why do people put up Yagis rather than quads? Well, they're a more elegant looking antenna for one thing, and they give good performance. Quads have more wind resistance typically than the Yagis do also. Approximately how long is each side of a quad antenna reflector element? If the driven element side is a quarter wavelength and the reflector has to be bigger, then it's going to be slightly more than a quarter wavelength, isn't it? Slightly more than a quarter wavelength. How does the gain of a 2-element delta loop compare to the gain of a 2-element quad antenna? They're about the same. And the reason they're about the same is that they're about the same antenna, they're just in a different shape. If you go all the way around the perimeter of a quad antenna, you have a full wave. If you go all the way around the perimeter of a delta loop, you have a full wave. Here the sides are a third of a wavelength instead of a quarter of a wavelength. Some advantages of the delta loop. It's easy to make a delta loop that you just hang from a pole, like you see here. If you want to make one that's on a boom so you can rotate it easily, you can do the same thing here. You can also make multiple elements, reflectors, the radiating element or driven element, and then directors, the same as on the Yagi. Approximately how long is each leg of a symmetrical delta loop antenna? Third of a wavelength long. What happens when the feed point of a quad antenna is changed from the center of either horizontal wire to the center of either vertical wire? Okay. What happens is that the polarization of the signal changes. The polarization of the signal changes from horizontal to vertical when you change the feed point to from the horizontal leg of the antenna. Here you're feeding the horizontal leg. If you instead feed the vertical leg, then you'll have a vertically polarized signal. For high frequency, it makes no difference whether you have a vertically or a horizontally polarized signal in most cases. But you can change the polarity on the quad antenna by changing where you put the feed point. To do that with a Yagi, you have to turn the whole antenna 90 degrees on its side, the way we normally think of an antenna that size, to make it into a vertically polarized antenna. What configuration of loops of a two-element quad antenna must be used for the antenna to operate as a beam antenna, assuming one of the elements is used as a reflector? The reflector element must be approximately 5% longer than the driven element. And we've talked about that before. They've had a whole bunch of verbiage here to try to mess up your mind. If you remember that the reflector has to be a little bit longer than the driven element, you will be fine. How does the gain of two 3-element horizontally polarized Yagi antennas spaced vertically 1/2 wavelength apart typically compare to the gain of a single 3-element Yagi? Okay, so we're talking about the same kind of antenna here, 2 of them instead of 3 of them. It doubles the gain, and doubling the gain is about 3 dB higher. Remember, doubling power is 3 dB. And here you see the two stacked, horizontally stacked antennas, and that doubles the power, or doubles the gain.